Now we're going to look at problem 10.8, which is if a particle is projected vertically upward to a height h above a point on Earth's surface at a northern latitude of lambda, show that it strikes the ground at a point 4/3 omega cos lambda square root of 8 h cubed divided by g to the west. Neglect air resistance and consider only small vertical heights. Okay, so what we need to do is figure out what the effective force is. So the effective force is going to be this real force minus the mass times r double dot, which is the acceleration of this frame, plus omega dot cross r, which is the angular acceleration of this frame crossed with its displacement, plus omega cross r, which is this centrifugal acceleration, and 2 omega cross vr, which is the Coriolis acceleration, Coriolis force times, with mass included. Okay, so let's figure out what is included in this and what is not. So we don't have a frame that's accelerating, so this one goes away. We also don't have the Earth accelerating or slowing down in its rotation, so that one goes away. But what's left behind is going to be the centrifugal force and the Coriolis force. Now, the question's only actually asking about the Coriolis force, so we'll go through that, but also it seems like there should be some centrifugal acceleration that we have, or centrifugal force we have to deal with, so I'll also deal with that, and then I'll compare when one is greater than the other. So if we assume that we only have to deal with small vertical heights, then that means that this r is going to be approximately constant compared to the radius of the Earth. And we're saying that this thing is mainly just firing upwards, and so that's going to be z hat. Okay, so let's deal with Coriolis to start. So this is going to be our VR term. So what is this velocity? So we're standing, on the surface of the Earth at some latitude lambda, or from the pole theta, and we're firing something straight up, straight away from the center of the Earth. So this thing's going to have some initial velocity, and of course it's going to go up, and then eventually this thing's going to come back down, and this maximum distance it travels is going to be some height h. So this velocity is going to be in the z hat direction, and we're going to have some initial velocity, but because of gravity it's going to pull it back down to Earth. Okay? So omega cross VR, we calculate the cross product by the determinant, x hat, we have minus omega cos lambda. So how we set up the determinant is we have the different directions that we have to deal with, x hat, y hat, z hat. The component of omega is in the x direction minus omega cos lambda, as we calculated in class. The y component is 0, and the z component is omega sine lambda. We calculated that in class, and so we never have to really calculate that again. You just have to know that that's what the answer is. And then we're firing this up in the z direction, and so that means that this velocity doesn't have an x component, doesn't have a y component, but the velocity has a z component. So to calculate this cross product, we use this determinant, and what we get is y hat, or negative y hat, times negative omega cos lambda times v naught minus gt. Okay. So we also have to deal with, we also have to know what the real forces involved are. The real force is going to be gravity. So the actual real force that we see is going to be mg, which is going to be negative mg in the z hat direction. And this we'll use as g naught because this is the real gravitational force. Now, as I mentioned, that just takes care of the Coriolis force. Now we can also take care of the centrifugal force. And so that is the omega cross r term. So how do we calculate that? Well, what we need to do first is calculate omega cross r. So we set up our determinant. We have the x-axis, the y-axis, and the z-axis. We have, because we're on the surface of the Earth, omega is always negative omega cos lambda in the x direction. There's no omega component in the y direction, and the omega component in the z direction is omega sine lambda. Now r is from where we're standing on the surface of the Earth, and so this radius, this r, is going to be the radius of the Earth. So there's nothing in x, there's nothing in y, and in z we just have the radius of the Earth, and so what we get is y hat omega, the radius of the Earth, and cosine lambda. So now what we need to do is actually calculate the centrifugal force term, so that's omega cross r. So we set up this determinant again. We have x hat, y hat, and z hat. Then again we have the omega component, which is negative omega cos lambda 0 and omega sine lambda. This is always going to be omega when we're on the surface of the Earth, which is why we'll always have this kind of similar form whenever we're on the Earth. If there's some other object, if we're on, say, some other accelerating thing, like say if you're in a car that's taking a turn or something like that, that will have a different omega. But because we're on the surface of the Earth, we'll always have this omega set this way. And now what we need to do is put in the omega cross r term, and so we have 0. We have the y hat component, which is omega times the radius of the Earth times cos lambda, and we have no z component. And so what we get is negative x hat omega squared times the radius of the Earth times cos lambda sine lambda minus omega squared times the radius of the Earth, right, cos squared lambda, and this one is in the z hat direction. Okay, so this is centrifugal component, and this one here is the Coriolis contribution. So the total effective force then is going to be mg mg naught in the z hat direction minus m, and we get negative omega squared re cos lambda sine lambda in the x hat direction and cos squared lambda in the z hat direction. And we'll have the Coriolis component will be 2 omega cos lambda v naught minus gt. Okay? So let's break this down into its constituent components. And we have z hat is going to give us negative mg naught plus m omega squared times the radius of the Earth cosine squared lambda. And notice that, and the x component plus x component, m omega squared times the radius of the Earth cosine lambda sine lambda. So notice that these components here don't actually depend on the motion of this particle or of this projectile that we've launched, and so this is always going to be the centrifugal force. So this is independent of its motion. So this would be the same as calculating the force on like a plumb line. And then we also have this y component, and this is dependent on the Coriolis force. Okay. So in the z direction, we have z double dot of t is negative g, and so we get z dot of t is negative, v naught minus gt. So we're calling this g. And we have z of t is equal to v naught t minus 1/2 g t squared, which assumes, of course, that z is equal to 0. So we're firing it from the ground. You can calculate what the maximum height is by two ways. You can use conservation of energy. So conservation of energy is the easier way. And what you get is 1/2 mv naught squared is going to be, so the kinetic energy is going to be equal to the maximum potential energy, so that's mgh, or what you get is v naught equals the square root of 2gh. Conversely, you can say from the equations, so from Newton's equations, we can say that z dot of t equals 0 when we're at height, at h. And so that's telling us that we have v naught minus gt is equal to 0, or t, we're at height h when we are at time v naught over g. when we don't have any friction. And then you stick this in for the z at this point, and so that's going to be v naught over g minus 1/2 g v naught over g squared, and that equals h, but you calculate that what you get is v naught equals the square root of 2 gh. So you can use either Newton's laws or conservation of energy, just like we could use Newtonian mechanics or Lagrangian mechanics to solve problems. You can do the same thing, you should get the exact same answer. Whichever one's easiest for you. And of course, this means that it'll fall back to Earth. At time t, and I'll call it tg for it hitting the ground, 2v naught over g, due to the symmetry of the problem. Okay, so we have this effective force. So what we want to do then is calculate from this effective force the motion of this projectile and how much it moves while it's in the air. So we have x hat direction that we need to calculate, and we have y hat direction that we need to calculate. So it turns out the y hat direction, you can see from the v naught minus gt, also from the factor of 2 there, that that's going to be the Coriolis term. And so that's what your textbook uses, so I'll calculate that one first, and then I'll show what the x term yields, which is from the centripetal centrifugal acceleration, or centrifugal force. So we do the same thing. We have y double dot is equal to negative 2 omega cos lambda v naught minus gt, and y dot then is negative 2 omega cos lambda v naught t minus 1/2 g t squared, because we're of course integrating, plus, I should say, v of y at 0. But of course we're just firing this thing straight up, so this is going to be 0. And then we have y of t. It's going negative 2 omega cos lambda, and we'll have 1/2 v naught t squared minus 1/6 g t cubed plus y of 0, wherever that initial position was. Okay? You'll notice from how the question's set up that it lands at the ground at a point away from where you start, and so what we'll be taking is the final minus initial, so that y0 will go away. Okay, so now y at tg, which is the time when this thing hits the ground, will be minus 2 omega cos lambda. What we have is, we can get rid of the 2. So we get rid of that 2, get rid of that 2, and change that to a 3. So we get v naught, and then we saw that this hits the ground at 2 v naught over g. So we substitute that in, and we get 4 v naught squared over g squared minus 1/3 g. And this gives you 8 v naught cubed over g cubed, so that cancels with that g, plus y naught. Okay. Now, from what we had before, we said that v naught equals square root of 2gh, and so what we have here is v naught cubed over g squared. And so what we get is 8 g cubed h cubed over g to the fourth. And that gives us 8 h cubed over g. And that's going to be that part in our answer. That's where that comes from. So what we get is 4 minus 8 thirds. And so we get 4 thirds omega cos lambda. We have a minus sign out front. Oh, I don't know what happened there. We have a minus sign out front. And then we get this 8h cubed over g. And this is in the y hat direction. So if you remember from how our Earth is set up, y hat points to the east. And so what this means is plus y naught. So we get a change in y is going to be 4 thirds omega cos lambda square root of 8h cubed over g to the west. All right. But this part didn't consider centrifugal. So let's look at centrifugal acceleration, or centrifugal force. Centrifugal. So what we have, remember we'll also have this contribution to the x hat direction. So the z hat direction, we've just said that this g is reduced by an amount from g naught. But in x hat, we have x double dot of t is going to be omega squared times the radius of the Earth times cosine lambda sine lambda. And so x dot, we can easily integrate this to get omega squared times the radius of the Earth cos lambda sine lambda plus initial velocity in the x direction. But again, we're firing this thing straight up, so that's just going to be 0. And so x of t, I guess or x of t in general, I should say, is going to be 1/2 omega squared times the radius of the Earth. Oh, I forgot the t here. Times cosine lambda sine lambda t squared plus whatever this initial position was. So we do the same thing. X of t g is going to be 1/2 omega squared times the radius of the Earth cosine lambda sine lambda. And then what we had before was tg is 2 v naught over g. And so this is going to be 4 v naught squared over g squared plus that initial position. And what we had before was v naught squared over g squared is going to be 2gh over g squared is going to be 2h over g. So that means the change in the x direction is going to be 1/2 omega squared times the radius of the Earth times cosine lambda sine lambda, and we're going to have 4 times 2 is 8, and that's going to cancel with this 2 here. So maybe I'll just cancel this, and so this will give us a 4, and we'll have h over g. And what direction is this? This will be south. Okay? So, if you look at the, this is due to Coriolis. and this is due to centrifugal. You can see that they both have, they have varying contributions, but they don't actually have the exact same form. And so let's put some numbers in this. So let's say we're at about 45 degrees. So I think in Windsor we're at 42 degrees. I think Toronto is something like 43 or 44 degrees. So maybe we're like the north end of Toronto. And so say lambda is equal to 45 degrees. Then that gives us an easy number that cos lambda is equal to the same as sine lambda is going to be 1 over root 2. The radius of the Earth is 6,371 kilometers. And of course, the rotation of the Earth, as you know from your assignment, is 2 pi over 1 day. And this is 7.27 times 10 to the minus 5 radians per second to the minus 1. Okay, so if we put in these numbers, delta x is 6.86 times 10 to the minus 3 times the height, and delta y is going to be 6.19 times 10 to the negative 5 height to the 3 halves. Okay? Or let's look at these relative ratios. What we get is 1.1 times 10 to the 2, 1 over square root of h. So that means that this delta y is going to be greater than this delta x when the height is greater than 12 kilometers. So 12 kilometers is about how high planes fly. So a plane normally flies at about 10 kilometers or so. So maybe if there's lots of turbulence or something like that, they fly a little higher. To get this high, I calculate that the initial velocity has to then be greater than 485 meters per second. If you remember, it's about 330 meters per second is the speed of sound. So you're going about 1.5 times the speed of sound, fired from sea level, which is about the speed of a bullet, actually. So, of kind of like a slow bullet. So, but the point is that as this thing travels up, it will move to the south, do this centrifugal acceleration or centrifugal force, and it'll also move to the east, it'll also move due to the Coriolis force to the west, and so that thing will actually come out of the board towards us. So if we fire something straight up, say, straight up in Windsor, then this thing's going to end up in Toledo or something like that, depending on how high we fire this.